Hello, everyone. I'm so honored to be here and to show our work. And today my topic is FaceCaps for facial expression recognition. And there are four parts of my presentation. Firstly, I will introduce the background of facial expression recognition. And after that, I will describe the details of the proposed method and show some experimental results. And finally, I will provide a conclusion. So let's start with the background. So the facial exploration are one of the most essential means for humans to express intentions and emotions in the process of communication. And due to the applications of exploration recognition in different fields, such as the medical treatment, intelligent counseling systems, exploration recognition has been widely studied. So the facial expression recognition aims to recognize human emotional states, such as surprise and sadness, based on a facial image. And in recent years, many methods have been proposed to solve this task. We can divide into two classes. And first one is a static image facial expression recognition. And the second one is a dynamic sequence facial expression recognition. And despite the progress made, the automatically recognizing facial expression with high accuracy remain a challenging task. And in this work, we focus on the static image-based approach in which feature representations are learned using only spatial information from the current single image. And recently, many computer vision tasks, including the face recognition and the facial expression recognition, have achieved successful results through the application of convolutional neural networks. And also the powerful feature representation learning capabilities of CNNs have contributed to the development of facial expression recognition. There are still some problems need to be solved. First one, a lot of data is needed to train the CNN module to avoid the overfitting. However, the existing facial expression data set is not enough to train a neural network with a deep architecture. And in addition, when the common factors such as lighting combined with facial expression, which requires a better learning structure to learn the powerful feature learning abilities and to distinguish the interclass differences. So recently, Hayton proposed the learning capsules, which provides a new perspective on feature learning. And capsule nice address the classical problem in image recognition. Images that have all the right parts, but they are not in the right spatial relationship. So here is an example. In a face, the precision of the mouse and one ear switched. And for image recognition, capsule networks use the fact that while viewpoint changes have nonlinear effect at the pixel level, they will have the linear effects at the part or object level. So it's the capsule network is helpful to provide the exploration specific representation because it can learn the spatial relationship. So the capsule network consists of only one convolutional neural network layer and one fully connected capsule layer. So such a structure limits its feature learning capability. So which means it's not deep. So although some efforts have been made, it's generally agreed that the capsule network is hard to become deeper, like CNN. So in our work, we propose to combine a capsule network with a FaceNet-based embedding module for the facial expression recognition, named the FaceCapsule. And the FaceNet is a face recognition system developed in 6 years ago by the researchers from Google and achieved the state-of-the-art results on a range of face recognition data sets. And it can be used to extract high-quality features from faces. We called face embedding. So in our work, we first use the facial feature information learned from the fine-tuned FaceNet to simulate the high-level neurons of the capsule network. Such modeling can naturally be used as feature-level regularization so that our model can quickly to learn the rich facial feature information. And also we improve the discriminative of the land features by building a 3D convolutional based dynamic routing with the capsule network. So we use each capsule to describe the image representation. And also each capsule learns to recognize the defend semantic viewpoint of the class. So in other words, each capsule means each kind of the facial expression. And also with the out capsule representing the class, this network can learn the deep high-level feature representation and also to elevate the turbulence of irrelevant noise information. And moreover, due to the inherent increases in the model capability, we propose target reconstruction rules to enhance the regularization and reduce overfitting. In our proposed architecture is in the figure B part, in which the class-independent FC capsule layers takes only the active vector of the predicted class. And we apply the MTCNN to achieve the face detection for the database. And during the training process, we used an ADAM optimizer and set an intentional learning rate to 0.0001, which is reduced by half after each 20 epochs. And we implement the proposed method in the PyTouch framework. We report the average of 20 rounds as the final experimental results. To help analyze our method, we evaluate on 3 public data sets. And first one is RAFDB. This data set is a real-world database that consists of 7 basic emotion classes and for evaluation and the 15,339 images are used, are divided into 2 parts. And the first part is for training and the rest is for testing. And the second data set, SFEW, the image from this data set are displayed in a real-world environment. And there are 3 sites in this data set, and 1 training, 1 validation, and 1 testing. And each image is assigned to one of seven exploration classes. The third data set is CK+. This is the most widely used live-controlled database for evaluating the facial exploration recognition methods. And in this database, it has 6 basic explorations and 1 contempt exploration has been labeled from 327 video sequence belonging to 118 persons. And so to evaluate the method, we designed 2 baseline networks. And the first one is an inception residue net V1, and the second one is a capsule network. And from this table, we can observe that compared with the capsule network, our methods outperforms by a large region. It almost 10% and 4.7% for RAF and SFEW too, respectively. And this table also summarizes the results of our method from the previous methods. And also the most of the state-of-the-art method enhance their feature learning ability by using both global and local information. The performance of our method is outperformer compared with the other method in currency. And also the difficulties with the SFEW data set is further evidenced by the results in this table, where our proposed methods obtain a competent result. Okay, so we also report the result on the CK plus data site, and there are some mistakes. And in our paper, our proposed method performs well in the recognizing the facial exploration on static image from the CK plus data set. And this is a libel control data set. It seems simple than the RAFDB and SFEW data set. And we test the method on the 2 pictures, which is randomly selected from the network. And we can see the input image after we to extract the feature from the input image, our method can to classify this picture to the angry. And the second one, this input image is means is a side. So the model can classify the facial exploration in a high occurrence. So from these experimental results, we can have some observations. And firstly, the proposed method achieve here occurrence as a dynamic routing between the capsules is employed to obtain the spatial relationship. And also we proposed the target reconstruction loss enables the model to learn the differences between the different facial explorations. And therefore, our method with the 2 enhanced modules improve the facial exploration recognition task. And however, I think this work have some limitations. And the first one, the parameters of the capsule network is we have a lot of parameters. So running the model spent a lot of time, and also each capsule it represents 1 facial exploration. So if the number of the facial exploration increases, the parameter will increases as a lot. So on the second one, I think the method only tests on the static image. So in the future work, we will improve our methods and try to test it on the video-based data set. Okay, so this is all of my presentation. Okay, thank you for your listening. Any questions?
Okay, thank you very much, Fangyu, for your very interesting presentation. Any questions from the audience? Nope. Okay, Fangyu, let me ask, the first questions here is, did you change or the objective function of the capsule network for your FaceCap?
No, I didn't change the objective functions, and I use the original functions during the training. And however, we design a new reconstruction loss.
Yeah.
It's just
Yeah, I don't see the loss function there.
Yeah. We design a new reconstruction loss.
Okay.
It is just corresponding to the input, but the equation is the same with the original loss function.
Okay. Okay, I understand. Okay, so you haven't included the loss function here in your slides, right? Have you? Yeah. Okay. Do we have other questions from the audience? Okay. Let me ask you the final questions. Sorry, Fangyu. How about your baseline network? Did you try different baselines, or did you ever do the so-called ablation study, which means you change the parameters of network and just remove some layers, then you see the results. Did you ever do that experiment?
We designed two baseline network, and the first one we use the capsule network, and we don't use the FaceNet. We directly use the capsule network to train, use the training data to train the capsule network. Yeah, this is original network. And the second baseline is we use the inception resonant night network. Okay, so inception resonant net V1. Yeah, these are two baseline networks.
Okay, yeah, thank you. Thank you very much. And looks like nobody in the audience likes to ask questions. Okay, cool. Thank you very much once again, and Fangyu, and for your presentations. Now.